Do you have in Discord this formula sheet opened and in front of you? Okay, I see an acknowledgement. That's good. This is as concise a formula sheet as has been constructed so far for our studies. It starts off with series circuit formulas, and we have parallel circuit formulas. In the series circuit, we start off with voltage divider, and then we have the currents all being the same. We have the voltages totaling V1, V2, V3, adding up to V total. Same thing with resistors, they're summed, power is summed. And then you have Ohm's law formulas for IT, V, and let's see, in the parallel, we have the current divider formula and what is equal. So those you should know. We have some power formulas. Kirchhoff's voltage law, KVL, algebraic sum of all voltages in a loop must equal to 0. And Kirchhoff's current law, algebraic sum of all currents entering and exiting a node must equal to 0. Conductance and resistance are reciprocal concepts of each other. So the less resistance you have, the more conductance you have. So they are behaving opposite of each other. The top of the next one, capacitance. Capacitance is reported in farads. What do capacitors do? They store energy and they block DC, but they pass AC. Formula for capacitance we didn't emphasize, and we won't have that as part of our final exam. The formula for farads we didn't emphasize, that will not be part of your final exam. Capacitor in an equation, neither that. The capacitance formula that you do need to know is your RC time constant, where tau is equal to R times C, and that's shown right in this area, right? I'm pointing to it with my mouse. I don't know if you can see where my mouse is pointing at. Capacitors in series, you use a reciprocal formula. Capacitors in parallel, you use a summing formula. So in this regard, capacitors in series and parallel behave oppositely of those with resistors. Inductance, the inductors in series, inductors in parallel, they behave similarly to the formulas you're accustomed to for resistors. So in series, your inductors sum, and in parallel, your total inductance is reciprocal formula. The only formula that you, let's see, the concept of inductance, it is measured in Henrys. The job of the inductor is to store a magnetic field. It blocks AC, but it passes DC. We have a time constant formula, which we've played with before, so you should know how to do the time constant. And then we will not be calculating inductance in a coil based on this formula, L is equal to N squared with a constant shown as micro A over I. We will not be using that formula. Now, transformers, you should be well practiced with transformer formulas. V primary over secondary is equal to turns primary over secondary equal to current secondary over primary. Frequency is the reciprocal of period, and period's the reciprocal of frequency. That's shown here. Then you have on the second page, converting to AC values, where you go from peak to RMS, RMS to average. And these are approximations. I wrote down an approximation, 0.707 times peak. We know we're going to use the square root of 0.5 for greater degree of accuracy. The 0.636, again, is an approximation. You know we're supposed to use 2 pi over R, 2 pi over, then you have average, okay, then you have reactance formulas, X of C, X of L, and impedance. And then your SOHCAHTOA relationships are shown here, and your Pythagorean theorem formulas are here. I would hope that all of these are already in your journals. Anything that's in your journal you will be able to use as part of your final examination resources. So if they are not already in there, you want to make sure you supplement your formulas in your journals with any of these that are not already in your journals. Any question on the formula sheet? Okay, let's move on. In the review session, I wanted to help you reconcile filters. And so if you were to see a filter circuit or something of a filter circuit that you haven't seen before, how do you reconcile it? So let me go and switch modes here. Be something like this. You may have an AC circuit, you may have a capacitor, you may have an output tap, so V out goes here, and this may have a RL to ground, and this also goes to ground. So you may already have this, and you may, somewhere in your journal, say, oh yeah, I've got the picture of the filter, and it's supposed to be an LPF or an HPF or whatever. But how do you actually reconcile this? How do you, without looking it up, how do you understand how this thing should behave? And the way you understand how this should behave is this guy behaves very, very much like this. It behaves like a variable resistor. Okay, so that is a symbol for generic variable resistor, RL. Okay, and this will have, RL is in ohms, of course, and then this guy is also in ohms. So what you have, if you redraw this conceptually, doesn't this look like this? Where this is your RL, load resistor, and this is measured in units of ohms. This is your V out, and then this is your X sub C, measured in units of ohms. And it's drawn as a variable because it does change. What causes XC to change? What causes XC to change is your reactance formula. If you remember, X sub C is equal to 1 over 2 pi F sub C. So frequency right here, as it varies, will cause X sub C to change. But because frequency is in the denominator, X sub C is over here on this side, they are inversely proportional. So what happens is, as I change frequency, X sub C will change. Now, think of this solely as a simple voltage divider. I can have several different scenarios. Suppose I have, in this particular case, and here's my out. So suppose I have low ohms, and suppose I have high ohms. If I have low ohms on top and I have high ohms on the bottom, what will my V out be? Will my V out likely be high or low? V out's going to be measured across the last ohms to ground. So what do you think, Jacqueline? What are your thoughts on this?
I think it would be low.
Let's test that, okay? Let's hypothetically put in some ohms and test that. So suppose for a moment this is low, and let's call this 1 ohm. And this is high, and let's call this 9 ohms, okay? So that would be low compared to the 9 ohms, yes? And so if we're starting off with 10 volts, and let's call that AC because this is an AC source, then you do your voltage divider. How much voltage will be on the output pin based on this? How do we do a voltage divider on something like this? This would be VRX is equal to RX over RT times VT. Wasn't that our voltage divider formula? Okay. And as that's our voltage divider formula, the unknown resistor, or the desired voltage is going to be across the 9 ohms. So wouldn't this be 9 over 10 times 10 volts? So VRX is my V out. So in this particular case, my V out is going to be equal to 9 volts, yes? And isn't that the majority of my voltage? So in this particular case, it's not going to be low, it's going to be high, right? So that as this tap is measured across the last set of ohms going to ground, that's where the majority of the resistance is, that's where the majority of the voltage will be. So in this particular instance, it will be, V out will be high, okay? So when this is low ohms equals high V out. Now, suppose I draw this here, and I think we can extend this. Yeah, we can extend this. So suppose for a moment, again, I have my 10 volt source. And suppose I have, they are the same, 5 ohms and 5 ohms. What will my V out be? G?
5 volts.
Okay, so measuring across here, this would be 5 volts. All right, so here, if my X sub C, because this is my X sub C, if my X sub C equals my R, then V out equals 1/2 V source. Is that right? Now, I'm going to give you a third scenario, and here's the third scenario. Suppose I have 10 volts, and because this guy is variable, now this guy is 9 ohms, and here's my V out. And this guy is 1 ohms. So now my R is low, and my X sub C is high. So what will my V out be in this particular case? My V out, what would it calculate to be? Jacqueline? Take the 1, divide by the total of 9, plus 1, times the 10.
So that would be 1.11 volts.
No, should only be 1 volt. If we do this, this would be 1 ohm over 10 ohms times 10 volts. And that's what will give us the 1, okay? You're not dividing 1 by 9. It's R total, which will be 10, okay? Because remember the voltage divider formula, VDF is equal to my Rx over RT times your voltage source. So it's got to be RT in the denominator, which in this case would be 10. So in this particular case, when X sub C is high, then your V out is equal to low, okay? So we have some summary concepts here. The summary concepts, if we go back to this first page of our notes, when my X sub C ohms are low here, if this is low, my V out is going to be high. When my X sub C is equal to R, then my V out is going to be half of my voltage source. When my X sub C is high because of where it is, my V out is going to be low, okay? And so how do we, when we look at all of these put together, how do we reconcile how the original circuit behaves with respect to a cap? We know that the cap will change its X sub C based upon the reactance formula. So let's go ahead and look at the frequency response graph. Remember, this is called an FRG, frequency response graph. That's the final question. What's an FRG? And it is the horizontal axis. It is in what units? F is in units of hertz. And the vertical one probably be voltage, V out. Now, you happen to have low frequencies, so low frequencies. So what happens at low frequencies when F goes small? Remember, these are inversely proportional. When this goes small in the denominator, what happens to x sub c? Does it get small or does it go up?
Go up.
Luigi says it goes up. Yusuf, what do you think? Up also. There you go. So x sub c goes up. X sub c equals high. But look at where the capacitor is. If the x sub c goes high, like what we have over here, comparison to the R, so what will happen is your RL equals low and your V out equals low. Is that right? When x sub c is high, compared to your R, 9 ohms compared to the 1 ohms, when this is high, 1 ohms, where the V out's being measured, will give us what we would call a low output, 1 volt compared to the full 10. That's going to be pretty low. So we can make this summary comment on this side of our FRG. All of this is true. So when frequency is low, your x sub c is high. If your x sub c is high, because of where x sub c exists, your RL will be low. And because your output is tied across RL, your output will also be low at low frequencies. Now, what happens on the other side? On the other side, you happen to have, and I'm running out of space here, I'll do this on a separate piece of paper and make this a little bigger for all of our benefits. How about that? That's okay. I'll just redo this. Right here and right here. Frequency in units of hertz and V out. So we said on this side, frequencies equals low. Therefore, x sub c equals high. And if x sub c goes high, we said that in comparison, RL is low. And if RL is low, then your V out is also low. Now let's see what happens on the high frequency side. On the high frequency side, you write F is equal to high. Therefore, X sub C is equal to low. Isn't that right? If you look at the capacitive reactance formula, if this increases in the denominator, it'll make your X sub C go small. So frequency high will make X sub C go low. And where is X sub C in all of these illustrations? X sub C low, 1 ohm compared to 9 ohms. Well, our V out is tied across the R, and the V out is going to be high in this particular case, as we surmised earlier. So let's go ahead and do that. X sub C low, so my RL is going to be high, and my V out is going to be high. And ultimately, this here and this here, through these steps, is what determines the shape of your frequency response graph. When this says right here that V out is low, I'm going to draw a little line right here that V out is low, because this is V out, and it clearly is low at low frequencies. Over here, my V out is going to be high. So what I'm going to do is I'm going to draw a line up here. And this is V out equals high. So when you go to connect these two dashes, with a nice S-curve, guess what kind of a frequency response graph you're going to have? The frequency response graph shows more signal, more output on higher frequencies. So what are we passing? What are we passing to the output? What are we passing to a speaker? So for example, here's a little speaker. So this evening I've got 2 classes, and they're going to be working on an amplifier, and they're going to be pumping sound out of this little speaker. So if they were pumping sound out of a filter network, what kind of sound would this speaker produce? Would it be low frequencies or would it be high frequencies? Yusuf, what do you think?
High pass filter.
This would be a high pass filter. Wei Ji, do you agree? Disagree? Okay, you concur? And Jacqueline, I saw your head nod earlier. Yes, this is an HPF by virtue of looking at the graph. So it begs the question. It's like, well, the original circuit was this. Does this mean that all resistor collector circuits in this network are all going to be high-pass filters? And the answer to that is no, not necessarily. We have to analyze each one on its merits. So right here, so suppose now I put the resistor here, and here's my V out, and I put the capacitor here. Now I have this circuit. And if I break this down into the different parts that we had done earlier, so let's say I have my AC source, I have my resistor, and then I have my V out, and I have my variable ohms. So this is my X sub C. And I'm going to do this 3 times. Like so, here. And that's the variable, because that's what will change with frequency. Do it one more time over here. And V out. And here, like so, X sub C. And what we're going to try to illustrate is what happens at low frequencies, at midpoint, and at high frequencies. So we already know from our X sub C formula, 1 over 2 pi F sub C, we already know at low frequencies, your X sub C is going to be high. At midpoint, your X sub C is going to be equal to R. And at high frequencies, your X sub C is going to be equal to low, by virtue of what we remembered from this formula. Now, where physically is X sub C? X sub C is on the output leg. X sub C is where the output tap is connected across. So whatever characteristics of X sub C is exhibited is going to be exhibited immediately at V out. So what I mean to say is this. If this is high, let's say this is the 9 ohms, and this is 1 ohm. And if this is mid, this is 5 ohms, and this is 5 ohms. And if this is low, then this could be 1 ohm, and this could be 9 ohms. So if you had to do the math, and you had to do a voltage divider between these two, my V out is the voltage across the 9 ohms over the total of 10 ohms, and you have a 10 volt source at the top, 10 volts here, AC, 10 volts AC, and 10 volts AC, then in this particular instance, won't the V out be high? Won't the V out be 9 volts? In the instance here, this is going to be 5 volts because it's mid. Over here, when you only have 1 ohm on the output, your X sub C is low because at high frequencies, when this is big in the denominator, X sub C is going to be small. So X sub C is low. So when this guy's low, how low? Well, let's say it's 1 ohm compared to 9 ohms. And if it's 1 ohm compared to 9 ohms, what's my V out going to be now? 1 volt. So my V out is going to be low. How does that plot on a frequency response graph? Well, let's go ahead and see. F in units of hertz and V out. And we already decided this side was low frequencies. This side was high frequencies. So based on low frequencies and high frequencies, at low frequencies, we said x sub c is high. So I'm going to make that notation here. X sub c equals high. Because x sub c is high, and x sub c is the output load, then my V out is going to be high. So V out equals high. On the other side of the spectrum, at high frequencies, because when the denominator increases, your x sub c will go low, your x sub c will become low. So we will write down here, x sub c equals low. And what happens to V out as a consequence? V out as a consequence also goes low. This is what you need to take with you in terms of your understanding. Where is V out at low frequencies? It says it's high. Where is V out at high frequencies? It says it's going to be low. So do I have a low V out right there? Do I have a high V out shown here? And if I go to connect these two with an S-shaped curve, whoa, what kind of a filter does this demonstrate? What range of frequencies is going to be passed to this particular speaker? It will be the bulk of the stuff underneath the shade, which is on which side of the graph? The low frequency side. So therefore, this must be an LPF, yes? And so the takeaway from all of this that I wanted to show you was not so much taking a drawing, making a picture of the filter and saying, okay, I can look it up in my journal because I have this and I can just look it up. I don't have to think about it. I really want you to think about it, where the position of the capacitor, whether we put it on the output or whether we put the resistor on the output, has a direct bearing on the behavior of the frequency response. It will, in one instance, it'll be a low pass filter, but if I reverse the components, it'll be a different filter altogether. So where's the challenge? The challenge in your final examination is not just looking up the picture and saying, okay, that one belongs to this and this one belongs to that filter. The challenge is, suppose you were to see something like this on the final exam. V out. Can you answer what kind of a filter that will be by your understanding of x sub c, 2 pi fc? Can you answer what kind of a filter this would be? Here's an R1, here's an R2, here's a V out, and here's an L. What do those do? And the way you reason it out, step by step, methodically, is everything we've done here in the first part of this FRG review. Is you look at the component, you look at the formula that derives the ohms, and is it inversely proportional or directly proportional? And if you don't remember the one for the coil, the X sub L in this particular case is 2 pi FL. So that means as this goes up, that goes up also. They are, these two, frequency and inductance, are directly proportional. Proportional, help if I spell that out. Proportional, yes, they're directly proportional. So as frequency goes up, X sub L goes up. As frequency goes down, X sub L will go down. Ooh, what the heck do I do with this? Easy schmeezy. I tell you, I'll just give you this one because you'll see other ones and you should be able to reconcile it exactly the same way. Okay? Because this L with frequency in AC becomes an X sub L. And then you have ohms going to ground. Ohms going to ground right here. And then you have a V out. And the most important part of this, is really this part of the leg here. That's the most important part of this to reconcile. And if we go ahead and do that, isn't this nothing more than something very similar to what I showed you earlier? RL2, and this is your X sub L. And depending upon how this behaves at different frequencies would determine its comparison to the ohms over here, what kind of V out you have. And I said I would work this out with you, I promise, and I will do that with you. Watch this. So we're going to do this, say, 3 different ways like we had done before. So we will have at low frequencies, at mid, and we can skip mid, we're really interested in low and high, at high frequencies. Okay, and so our divider looks something like this. So again, we'll start off with 10 volts AC, and over here we'll start off with 10 volts AC. So here's your V out. Here's your V out. Here's your RL2. Here's your RL2. Yes, RL1 does come into play, but it really is not that influential for our discussion. So here's your X sub L, and here's your X sub L. That's the variable. That's the part that will change. Your X sub L equals 2 pi FL. So at low frequencies, when frequency is low, what do you expect X sub L to be? X sub L is equal to, Jacqueline?
Low.
Low. Good job. And Yusuf, when X sub L is, when frequencies are high, X sub L will be equal to?
High.
High. But you take a look at where that variable capacitor, where that variable ohms happens to be for this inductor. It happens to be above my output. So we have to compare it with the load resistor. So if this guy's low, X sub L is low, then this would be, let's say, here's your 1 ohm, and here's your 9 ohm. Isn't X sub L low compared to RL? So what will my V out be in this particular case? How many volts?
9 volts.
9 volts. And compared to a maximum of 10, your V out would be high or low?
High.
High. And then over here, Jacqueline, when my ohms are high on top, well, let's throw in some hypothetical numbers. Let's say that this is 9 ohms, and let's call this 1 ohm. Isn't that high compared to 1 ohm? Yes, and these are easy numbers because they add up to 10. So what will my V out calculate to be, Jacqueline?
1 volt.
1 volt. And therefore, would my V out be considered high or low?
Low.
Low. So here you have a circuit that you've never seen before, but because you understand the principles of reactance formulas, you're able to reconcile this. And based on reconciling this, guess what? You can put that together into a really nice FRG. So frequency in hertz, right there. Here's your V out, right there. Here's your low frequencies. Here's your high frequencies. And what was the behavior? When frequencies are low, X sub L is low. So we have XL equals low. When frequencies are high, my XL equals high. And because the coil happens to be in the upper part of your voltage divider, the load resistor being on the lower part of your voltage divider, it makes your V out, 9 volts makes your V out what? High. So my V out in this case is high. Whereas on the other side, the converse is true, V out's equal to low. So how do I bar my lines on this graph? V out is high, goes way up there. V out is low, goes way down there. Connect these two with an S graph. What part of the frequency range is being realized on my speaker at this moment? It will
Low
be,
pass.
yes, precisely. This will be a low pass filter. Now, you haven't seen this filter before. Doesn't matter. You're going to see things you haven't seen before in the world of electronics. And the value of a good electronics technician is to learn to be flexible and learn to be creative and say, okay, here I have a challenge. I've never seen this before. This is not in my journal. What the heck am I going to do with this? Well, what is in your journal? What is in your journal should be these two formulas, one for X of C, one for X of L. And then you just change this to a variable resistance symbol like this. And then you just redraw it in the way that voltage dividers are very friendly to you. Just make it a stick from top to bottom. You have a 10 volt AC at the top. You have two things that are of consequence with the V out in the middle, and work it out from there. Okay? You can work it out. You can noodle things out. That's the challenge of the final exam. Okay? Because you will not see things that are exactly as you have seen before, but you are to apply the principles of what you have learned during the course of our time together and solve for fun and interesting stuff like, oh my God, I've never seen that. What am I going to do? Well, just like this one. Here you go. You might practice that and discuss this one right here that I've drawn inside this rectangle. And let's call this unknown filter number 2. Okay, we'll call this unknown filter number 2. And you guys should get onto the Discord and noodle this out between you guys with some good chat discussions and say, okay, we know what Co said. Co said to take these capacitors and do what? Change these into variable resistor symbols. Change the cap there to a variable resistor symbol. Change this cap here to a variable resistor symbol. Then, what did Co say? Well, because this is a capacitor, we're interested in using the capacitive reactance formula in the upper right-hand corner of this review sheet. And based on this capacitance formula, then we're going to draw a couple of stick diagrams, and the couple of stick diagrams will look something not dissimilar to these guys, okay? And you're going to have a V out sticking out in the middle of there somewhere. And you're going to reconcile fundamentally what happens when frequency goes low, what happens to X sub C, when frequency goes high, what happens to X sub C. Physically, where is the X sub C in this circuit, and how does that influence what's going on with respect to my output? Interesting. You can do it. So think about that with your classmates. That's all I'm going to say regarding filters. Spent enough time on that. I hope any remaining questions any of you may have regarding filters before I go on to the next. Okay, so the next topic that I'd like to review with you on our final exam is multiple secondary transformers. Okay, so multiple secondary transformers, because they're going to be part of your discussion here as well. And your multiple secondaries, okay, I'm going to have a primary. So here's my primary, iron core to be sure, and I will have an upper secondary right there. So I will have a V out 1, and I will have another one here, call that V out 2. And let's say my input in this particular case happens to be, I want to say 180 V RMS, and this is at 50 Hertz. And I'm going to give you some information here. I'm going to say this up here is going to be 12 to 3.2. And here, I'm going to say my output is, I want to say 210 VRMS. So we want to find out N1 for the lower, N2 for the lower. This 12 represents N1 in the upper, and this equals N2 in the upper. So we have the upper secondary that gives us V out 1. We have a lower secondary that gives us V out 2. So what do you have to reconcile with respect to all of this? You're going to have to reconcile, now I'm going to put in some load resistors to make it more interesting. And another load resistor here. And let's call this one RL1. And let's say RL1 is equal to 10 ohms. Keep it simple. And let's say RL number 2 is equal to 15 ohms. We'll keep that real simple as well. So we want currents, we want voltages, we want turns ratios, we want everything for all of this. Everything. Power, frequency outs, upper power out, lower power out, power in total, all of it. So how do you go reconciling something like this? Well, multiple secondaries are real world secondaries. Your computer power supply, those of you who happen to have, well, actually, even your laptops have multiple secondaries. But your desktop machines for sure have multiple secondaries because you have different voltages to go to different parts of your computer. Your drives, so those of you who have CV drives, they take a certain amount of voltage. Those of you who have hard drives, whether they're going to be solid state or whether they're going to be disk drives, they have very specific voltage requirements. The motherboard has voltage requirements. So you'll have multiple secondaries. So this is very practical. So let's break this apart. The best recommendation I have for you is this. My Nigerian fellow instructor, a fellow instructor from Nigeria, his grandmother had asked him, he says, Jonathan, his name is Jonathan, Jonathan, my boy, says, how does a man eat an elephant? And Jonathan said, I don't know. How does a man eat an elephant? Fork and spoon? He thought he was being funny. I would have said chopsticks. But grandma says, no. A man can eat an elephant only one bite at a time. So when you look at a circuit like this and you're shown a whole page full of things to fill in, don't freak out. You'll have scratch paper, lots and lots of scratch paper, okay? I will supply you scratch paper up the yin-yang, not to worry. And so here's the thing. Let's take this apart one by one. Let's just look only at the upper secondary and analyze it. And then later on, analyze what's happening for the lower secondary. Okay, so we'll just break it into two different parts. So if we look at the upper secondary, what do we have here? Well, I'll cover this up and let's take a look. We know our transformer formulas are V1 over V2 equals N1 over N2 equals I2 over I1. That's what we know. And that being said, we also know that F1 equals F2, and then P1 is equal to P2 if this were a single secondary. If it's multiple secondaries, your P1 is equal to P2 upper and P2 lower, okay? Let's just call it those. So these two powers added up together will give you the total power if we have multiple secondaries. Now, that being said, let's just deal with the upper secondary. So what do we know? Let's use this part of the formula. V1 over V2 equals N1 over N2. Mouth is not moving fast enough here. That's equal to 180 V over V2, which we don't know, but we know N1 is equal to 12, and we know N2 is 3.2. So you probably have this already because we're going to do what in order to solve for V2? The process is known as cross multiplication, yes? So when you cross multiply, let's go ahead and do that. The calculator. And so we should have 3.2 times 180 and then divide by 12. And so Weiji, do you have a number for us for V2?
48.
Okay, so V2, which is your V out 1, okay, works out to be what, 48 apples, 48 oranges, 48 what?
48 volts RMS.
There you go. Okay, so we have to speak and write the whole thing. If you just write a value, it is incomplete. Are we in agreement? We have 48 VRMS for V out number 1. This is the upper secondary. Upper secondary. So based on that, with a 10 ohm resistor, do we have enough information to calculate I2 upper? And Jacqueline, how would I calculate the current going through the upper secondary? What method would I use?
You could use Ohm's law.
Okay, and Ohm's law would be what over what to give me current?
The voltage over resistance.
Okay, voltage over resistance, and the voltage we just calculated was 48 volts
VRMS.
over 10 ohms. All right,
Yep.
so what will be the current in this case, Jacqueline?
4.8 amps.
4.8 amps RMS. Cool. So that's my I2 upper. Do we have enough information to be able to calculate power in the upper? Power in the secondary. Power 2 upper. Yusuf, how do I calculate power?
Voltage times current.
Okay, so V times I. Which V am I going to use?
48 volts.
48 volts. And what current am I going to multiply this by?
4.8 amps RMS.
4.8 amps RMS. So when we go to do this, 48 times 4.8, what do you calculate the power to become, my friend?
230.4 watts.
230.4 watts. And that's the power of the upper. Good job. Okay, so far so good. We're going to have to leave it at that and then now look at the lower. Normally, with a single secondary, we would be using this part of our formula, N1 over N2 equals I2 over I1, in order to determine the current in the primary. We're not going to do that in this case. We can't because we have two secondaries. So we have to wait. We have to be patient. So now what we're going to do, we're going to analyze what's happening in the lower secondary. What's happening in the lower secondary? Well, let's go ahead and look at my formulas. So my formulas were V1 over V2 equals N2 over N1 equals I2 over I1. So those are my formulas. Am I given an N1 lower? Nope. Am I given an N2 lower? Nope. Uh-oh. What do we do here? Question goes to Jacqueline. What do you think?
Use our voltages.
We're going to use our voltages. Cool. All right. Let's go ahead and use our voltages. My V1 over V2. What's my V1 in this case?
180 VRMS.
180 VRMS. Excellent. What's my V2 in this case?
210 VRMS.
210 VRMS. And if you go to calculate that, what does that calculate to become? Let's take the 180 divided by the 210 and see what we get. And what do you get?
857.14 milli.
857.14 milli. And that is 857.14 over 1. Is that not? Anything divided by 1 is itself. And we said that our V1 over V2 is equal to, I wrote this wrong, I1 over I2, N1 over N2. So equal to N1 over N2. So isn't this equal to, wouldn't this be equal to 857.14 milli over 1? Now do we have a turns ratio? Okay, now we know N1 is a specific number, N2 is a specific number if we had to put it into a fraction. Okay, so far so good. That's very helpful to us. Now, as that's very helpful to us, how then do we have enough information now to determine current in the secondary? How do I do, Weiji, how do I determine my current in the secondary?
V over resistant.
Okay, cool. So my I2 lower, because we had I2 upper a moment earlier, now I2 lower is a V over an R, and in this case it is 210 V RMS, and this is over 15 ohms. So what is the calculated current in this particular case?
14 amp IMS.
Works out to be, oh my goodness, I couldn't have planned it any better. 14 amps RMS, no decimals. So earlier we calculated 4.8 amps RMS in the upper secondary, but now we have 14 amps RMS in the lower secondary. Do we have enough information to calculate power in the secondary for the lower? Do we have enough information to calculate this USEF?
Yes.
And what formula would I use?
Your amps times volts.
Just like what we did earlier, right? Power of the upper was V times I, power of the lower is V times I. Except now my V is 210 V RMS, and my I is equal to 14 amps RMS. So my power in the lower works out to be what value, my friend? Yusuf?
0.94 milliwatts.
Are you sure it's milli?
2.94 kilowatts.
Okay, is there a difference between milli and a kilo? Yeah. If your paycheck was 2.4, 10 to the negative 3, you would probably say it's not worth the paper it's printed on. If, however, your paycheck for the week was 2.4 with a K, then you'd be running to the bank pretty fast, wouldn't you? Yeah. So is there a difference between the milli and the kilo? You betcha. And students like that when I bring in dollars and cents. All right, so we have a power in the upper, we have a power in the lower. Do we have a total power of both secondaries added together? P2U plus P2L, P2 upper and P2 lower. If you go to add these two guys up, let's go ahead and add these up. Plus 230.4 equals, so I end up with 3.17 kilowatts. Does somebody want to concur, verify, tell me I made a mistake? Okay, I got a thumbs up from Jacqueline, and Yusuf says yes. So we're all pretty happy that's my total power in my secondary when I add these up. Isn't that also, my friends, equal to P1? Ultimately, the power of the secondary, multiple secondaries, they have to add up. That is my total power. Once I have total power, do I have enough information? Do I have enough information to find I primary? How do I find the current in the primary? What method would I use? Jacqueline, you want to tackle this? Throw out a lifeline?
So N1 over N2 equals I2 over I1.
Yeah, but we have two
Would
different sets of N's.
I2 be the total currents added together? Same with the powers?
No. No, it would not. So let's try
Why?
a different tack. No, here's what it would work out to be. Well, we're gonna calculate it, and I'll show you the method, the for sure method where we can calculate this. Weiji, do you have the solution? The
Power
method?
over volts.
Okay, we're going to use Watt's law. Watt's laws, plural. There's 3 of them, if you remember. Let me put this here where we can see it. Watt's laws. We're going to see which one is applicable. You have a P, I, V, P, I squared R, V squared P R. Now those are Watt's laws. They work similarly. You use them similarly as you did with Ohm's law. As long as you have 2 quantities, you can calculate a third. So for this current that we're looking for, I1, you have, what are the facts? You have, we now have V1 and P1, yes? Because V1 is equal to 180 VRMS, and P1, we just calculated earlier, 3.17 kilowatts. So those are the 2 critical pieces that we now have. The turns ratios don't come into play in this particular case, and the individual currents, we'll see what's happening here in a moment, but do I have enough information to implement one of these circle formulas for Watt's law? And most likely be the first one, yes? So my I1 right here, I1 is equal to P1 over V1. And this is equal to 3.17 kilowatts over 180 VRMS. And Weiji, can you do us a calculation for us, please?
17.61 amps.
Here, and 17.61 amps. So 17.61 amps RMS. That is our current coming out of the, that has to be delivered into the primary. And if you go back to, Jacqueline, your rationale earlier, we had a current in the upper secondary that was 4.8, and we had a secondary current in the lower of 14. And if you go adding those 2 currents up and do something with turns, we're not going to quite add, they don't reconcile to be 17. So the best way of reconciling this current is to use Watt's laws. Find the power, the total power, which we did, find the total power of the 2 secondaries added together is equal to the power of the primary. Once you have they have to be the same. Once the power of the primary is known, then we can use Watt's law and derive the actual current that's flowing, okay? There may actually be a wonderful calculus type derivation of mixing the 2 sets of turns ratios and other things in order to find. There possibly is, and you'll find that in electronics, we have found already, there's several different ways of getting to the answer. I'm just looking for the simplest way of getting to the answer, all right? And there we are. Any questions on a multiple secondary transformer? So which one of these is a voltage step-up transformer? Upper or lower? Wait, gee, which one of these is a voltage step up? Which?
Lower.
Yeah, the lower secondary. This is my voltage step up transformer because we went from 180 to 210. That part is my voltage step up transformer. The voltage step down transformer is the upper secondary. The upper secondary, we reconciled the V out. The V out here worked out to be 48 volts RMS. So if you compare 180 to 48, then the upper secondary was voltage step down from 180 to 48, but the lower secondary is voltage step up from 180 to 210. So watch the terminology of the question very carefully when you see it on the final. And I'll say this, I'll reiterate during the course of the final and certainly at the beginning of the final, and that is any questions, any ambiguities that come up along the way, say, hey, Co, did you do something? Did you do a dyslexic thing over here? Like sometimes you do, and I might mix a number or something. If anything seems at all awkward or something might be misplaced in terms of a word or something, just call me over and say, hi, could you take a look at this? Am I to understand this works this way? And I'll just come over and lean on your shoulder and say, yeah, you're on the right track. Or, oh, wow, maybe I had a faux pas and I mistyped something and I have to let everybody in the class know there was a mistake somewhere in the new final, because I never use old finals. You guys always get a new final. Yeah, I might type something wrong. It can happen. All right. So that takes care of multiple secondary transformers. Cool. All right. Now, next on our agenda of things to discuss will be Kirchhoff's voltage law and Kirchhoff's current law. If we go back to our friend, remember superposition. Oh, we hadn't practiced one of those in a while. But if you remember in superposition, didn't we have in one instance a voltage here, a resistor here, perhaps a resistor over here, and then a voltage source over here, like that. You had an R1, you had an R2, and you had an R3. And there could have been more resistors, it doesn't matter. But you have two sources. And how do I know this is superposition? Well, it's not series aiding and it's not series opposing because these two guys are not in series. Flat out, okay? Immediately, they're not in series. So you're going to have to use superposition. And what do we do with superposition? Negate one, replace it with a short. Like so. And replace this with a wire. Neek, where the source was. Now you only have, oh, that's too simple. Oops, I did have a third resistor, thank goodness. Otherwise I'd be in a pickle here. So R1, R2, and R3. What do you do with this? Simplify it from 3 resistors down to 2 resistors. And if all of these all equals 100 ohms, give me an RT right now. Okay, we have one value of 150. Does Yusuf or Jacqueline have a different value? They're all 100 ohms. And in this redraw, what is my RT is the question.
150 ohms.
150 ohms. Yusuf, what do you think?
Yeah, I think it's 150 ohms.
Looks like 150 ohms. Okay. And so you run with it, you do your analysis, you do your current. So it would be here, here, right? Electrons flow here, hits this node. What's going to happen? It's going to split. Which way is the current going to split? Up through here, over to the right here, and here. So when you do your VIIR table, if we were to do a VIIR table, you would have for R1, R2, and R3, in this go around, you would have a value of some amount of current. Okay, let's say this is 10 volt source. 10 volt source. So find me the currents. This is 100 ohms, this is 100 ohms, and this is 100 ohms. How do you find the currents? You need the redraw. Because this guy works out to be 50 over here. This guy is a 100 ohms over here. And this is a 10 volt source. So how do I find my current that's going around in this particular loop? Isn't that going to be 10 volts divided by 150 ohms? And what's my current going to be?
66.67 milliamps.
66.67 milliamps. That would be correct in this redraw. Bring that information here. You have 66.67 milliamps flowing out of the source. You must have 66.67 milliamps flowing back to the source. How does the current split between these 100 ohm resistors that are in parallel with each other? How do
Evenly
they
split.
They split evenly, so divide by 2. 33.33 milliamps. So could we quickly mark the direction of current for R1? It goes to the right. The direction of current for R2 goes up. The direction of current for R3 goes to the left. And then the value is 66.67 milliamps, and then 33.33 milliamps, and another 33.33 milliamps. And are we done with this half of superposition? Done. Then you do the other half of superposition and you work on the same things. Find the directions, find the currents. What do you do in the last part of superposition? Algebraically add. And then you'll end up with some kind of loops. So here's a question. If we are to understand Kirchhoff's voltage law, KVL, all voltages in any closed loop must algebraically add to 0 volts. We know that. So if you had and I don't know what the final of this guy will be, but we can go ahead and pop in some numbers here. Let's say I have a VS1, I have a VS2. Let's say this one's equal to 10 volts. And let's say this one's equal to 15 volts. This is my R1, here's my R2, and here's my R3. So, if you were going to do some reconciliation here, let me do some fast number mental juggling here for a sec. Let's say this guy is equal to 6 volts. And minus okay, if you were to see this, can you determine several things? Can you determine VR2 and all polarities? Ooh. I'll give you a start. This is a plus and this is a minus. This is a plus and this is a minus. This is a plus and this is a minus. Based on that extra bit of clue, can you figure this out? Tick tock, tick tock. I'll put me on mute for just a moment while you cogitate. Okay, your time is up, and I'm sure some of you have figured this out. So, Jacqueline, you look very composed. You have a supposition for some value for us?
R2 is 4 volts.
R2 is 4 volts, and what leads you to think it should be 4 volts?
Because I've got a thought process, but also it pretty much has to be.
It has to be, according to?
KVL.
There you are. According to KVL, it must be 4 volts. You are correct. And as it is 4 volts, it must be 4 volts. Let's go ahead and do this. See if we can, it doesn't quite work that way. I wonder why it doesn't work that way. Because I wanted to have all of us, see all of us. But in any case, you are right. So we have VR2 is 4 volts. Now, how about the polarity across VR2?
The top of R2 is negative.
The top of R2 is going to be negative, and the bottom is going to be?
Positive.
Okay. I'm going to draw that in lightly, because if we do a loop equation, okay, so here's A, remember, here's B, here's C, D, E, and F. So if I do a loop, walk this through with me, okay? If I do an A, B, E, F back to A, and we draw a line because that infers a loop. So I'm going to write down loop, write down those sequence of 5 letters, and that tells us with a line across, we're going to go from point to point to point to point. So from here, I am going to encounter a what?
Positive 6 volts.
Positive 6, and then, so I will have a positive 6. And then from B to E, I'm going to encounter a what?
Oh, yeah, okay. So you're
Yeah.
going to, so
Go
really
ahead.
it needs to be a positive 4.
It needs to be a positive up here. You're right. That has to be positive. This has to be negative. And we have to have 4 volts here. Because as we come around from point B to E, we have to see a plus 4. Because from E to F is a 0, but from F back to A, we see the negative. So we add the negative 10. And according to Kirchhoff, that will give us a 0 right there, yes? Okay. So now we know the value of the voltage R2, and we now know the polarity across R2. Okay. All right, Yusuf, what do you think on R3?
What are you asking? The voltage?
Well, I gave you the voltage. What else is left? Polarities.
Yeah. So the right side of R3 will be negative,
Right side is going to be negative.
and the left side will be positive.
And that's going to be positive. Okay. Let's go ahead and do a loop. So here's another loop. And let's go B, C, D, E back to B. Okay. So from point B to C is a 0. How about C to D? We have a
Positive.
15, so plus 15 volts. Then from D to E, we have a,
Negative 11.
so we're going to add a negative 11 volts. And then from E back to B, we have a
Negative 4.
negative 4. So, my friends, does a positive 15 add a negative 11, add a negative 4, give us a 0 volts according to Mr. Kirchhoff? Is Mr. Kirchhoff a happy camper? I'm a very happy camper. Okay, everybody good with this kind of exercise? Okay, cool. All right, that takes care of Kirchhoff's voltage law. And then the last one I wanted to touch base on was Kirchhoff's current law. And so here, one more. just for good measure, out here. All right. And I'm going to show you 10 amps going this way, 2 amps coming this way, 3 amps going this way, 14 amps going that way, 12 amps going this way, 11 amps going this way, 16 amps coming this way, and here's the question mark. How do I solve this? Is there a method? Wei Ji, is there a method?
Yeah, we just put a column and then write down the in and out, and then we subtract them.
Okay. All right. So here's a cross. And we'll put one column is in and another column is out. Now let's go ahead and count for these one by one and see where they land, okay? So we start off with the 10. The 10 goes in which column, Wei Ji?
In,
Okay, with 10 here. How about the 2 amps?
out,
2 amps goes here. How about the 3 amps?
in,
3 amps goes in. How about the 14 amps?
out,
Out. How about the 12 amps?
in
How about the 11 amps?
again,
In for 11 amps. How about the 16 amps?
out.
Out. Okay, let's see what each side adds up to be. So Yusuf, what does the left side add up to be? The in column, what does the in column add up to be, Yusuf?
36 amps.
36 amps. Okay, Jacqueline, what does the out column add up to be?
32 amps.
32 amps. Does that give us, Jacqueline, the column and the value of our missing current?
Yes.
Yes. So what value in which column should I write down?
4 amps out.
4 amps out. I must have 4 amps added to 32 to give me the 36 amps. That must equal the 36 amps on the other side, yes? So 4 amps in the out column, 4 amps, and the arrow would be out. Was that a piece of cake or what? Now that you know a method, yeah? Kirchhoff's current law. Cool. All right, well, we covered all the hit points that I wanted to just, oh, not quite. There was one more. One more. Yes, 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 yes. And so here's another thought question, and then we'll wrap up with this. In which, comma, RC or RL, and I should preface this as series RC and series RL, does voltage lag current? Where is our solution for this? Wei Ji, do you remember?
No, I don't.
Jacqueline, do you remember?
Eli the ICE Man.
Exactly. Eli the ICE Man. Okay, now that's our clue as to where we find the solution. We use the memory tool, and the memory tool is called the mnemonic. The mnemonic was Eli the ICE Man. So I come back to the question, and you can help us out with this, Jacqueline. Series RC or series RL? In which instance does voltage lag current?
Series RC.
Series RC, because we have a C here, and voltage is the E, I is the current, and clearly voltage is lagging the current in a C circuit, so it must be my series RC. Bingo. Well done. That's how you reconcile this with the memory tool, Eli the ICE Man. So I will say this, in our 16 plus weeks together. This has been our most thorough, most in-depth coverage of very essential electronic circuit concepts for a strong, very strong foundation first semester that we have had ever here at Chabot. And it's not because I'm a good teacher or anything. It has nothing, I'm not. But the reason why it is because this is the first time we've ever had this class run the full semester with 2 meetings a week. One meeting 3 hours where we're in person, and then the other meeting an hour and a half on Zoom. We've never had that amount of time together in ESYS 50 before. ESYS 50 previously has only been an 8-week semester, 8-week course. And so how do we cover this content of this depth to this level of understanding in 8 weeks? It's been challenging. So I fought really hard for this course to be a full 16 weeks. And I commend you all for hanging in there and doing very, very well. I think you all will do very well on your final exam. There is a hands-on lab component that we will be playing with as well. What will that be? Well, there'll be some O-scope stuff. You'll be playing with signals and probably a phase shift exercise in the real world, not a multi-sim phase shift like what you've played with in the past, but probably a real phase shift circuit. So review your notes for your multi-sim phase shift exercises on how to calculate your phase shift in degrees. Look at that very closely because you're going to be doing something very similar to that in your hands-on lab final, okay? All right, my friends, we are at the appointed hour. I'm 1 minute over. Sorry for being so verbose. Any questions any of you have before we part company? Okay, if no questions, let me find, where's my button here? Button. Okay, back to here and then, oops, wrong button.